All right, there we go. Let me just adjust my monitor here. I mean, my second monitor. All right. Hey, everyone. Welcome back. Mm, with this stream, we'll be starting a new series, as you might have read the title. We'll be starting with learning data structures and algorithms. I'll get to it shortly, but before that, I understand that there was another power failure with my React stream, so that got cut off in the end. So I apologize for that. Let me see if there's something I can do to fix everything. I already have a UPS, so my system stays on, but it's my Wi-Fi which just get cut off, and the stream as well will gets cut off. But yeah. Anyhow, so right now let's come back to our stream, which is regarding data structures and algorithms. So as you might already be aware, DSA is kind of a spread out topic, right? I like to compare it with math, right? Because learning DSA is sort of like learning math, right? There is no like, if I just ask you to go ahead and learn math, there are a plethora of topics out there, right? There is no structure as such, right? Although you could get a structure by following someone else's recommendation and stuff. But I guess what I'm trying to say is that, simply asking you to learn math is like, yeah, it's not the best option out there, right? So, um, as you may already know, I'm also doing practicing code wars stream, right? So I don't want it to be confused with this. I'll still be continuing with the practicing code wars streams here and there, but that would exclusively be for code wars. Whereas in here, we would sort of be maybe we'll do code wars, maybe we'll do lead code, or we'll jump from topic to topic. It's gonna be it's not gonna be like my previous streams where I already have the source material available. I know what I'm gonna like learn, not where what I'm gonna learn, but where I'm gonna learn from. It might either be a YouTube video or something or the other. But I guess, since, as I previously mentioned, DSA doesn't really, it's kind of like trying to learn math. There are a plethora of topics out there. I would be jumping from topic to topic, video to video, maybe do my own Google search. Although there would be some sort of a reference point that I'll have, which I'll show you in a bit, but I just want to put it out there. This one is going to be a bit different. I won't be just doing a single course or nothing like that. It would just be like a mix of things. There would be practice involved. There would be a bit of articles, a bit of this, that, courses, YouTube videos, blogs, and obviously solving more and more problems and whatnot. Um, so, if you're watching in YouTube, I'll try to include all the links possibly, right? And let me try to figure out a way that where I can maybe post all the links somewhere, maybe on the GitHub repo for this, or we'll see. But just keep that in mind. This is gonna be sort of like unstructured way of learning. I'll be jumping around from topic to topic, but at the same time, it would be structured in a way, like maybe semi-structured. You can call it a semi-structured way. Now, here's where the structure part of that comes from. So, here, well, first of all, here's a site that I will recommend to anyone who wants to learn anything related to programming. It's a really useful one. It's called roadmap.sh. Well, that's the website. As you can see, there are a lot of roadmaps out here, and this is yeah, this is really good for someone who's into self-learning and stuff, right? You can learn all kinds of things here, right? All kinds of tech frameworks. I think they also have React in here. Yeah, obviously they have React. Yeah, there you go, React there. And they also have different languages, programming languages. They also have computer science as such, which would be interesting to look into. Right. Anyhow, the roadmap that I'm gonna use as a reference here, and again, not a reference doesn't necessarily mean I'll be following every single topic out here. Um, where is data structures? Ah, oh, there we go. Oh, I already had it open in the other tab. Anyhow, so this is what I'm going to be using as a reference. And I may or may not look at this content, but I'll be using this to know what I have to learn, right? But I may or may not use the content given from here. And I'll also be skipping a couple of topics. For example, pick a language. We already got that covered. Yeah, programming fundamentals, we can skip that and stuff like that, right? So again, keep in mind, this is gonna be a reference, but it's not gonna be a set in stone reference of any kind. I'll use this, but you use it to get the topics to learn, but I may learn it from somewhere else and just switch between here and there. You might find me do that a lot with this stream series. So anyhow, that was what, a long intro. So I've already taken a look at most of the topics here, and I believe we'll be starting off with algorithmic complexity, right? I sort of know what big O notation is. I know what linear time is, what like exponential time and stuff is, but we'll start with this as a refresher and then move on, right? So let's get started. So for this, I believe I'll be following. Let me just pause this so it doesn't start. Let me skip this ad.
Big.
Right. So I'll be doing this sort of. Oh, the roadmap. Oh, it's actually a YouTube channel. Oh, I didn't know that. Yeah, I'll be let's start with this video, right? It's gonna be a 10-minute video. It's a great. I feel it's a great summary, right? Once we finish this, let's jump on to a bigger course from Free Code Camp, right? And yeah, let's do this first, and then as the stream goes on, we'll switch between topics. So here we go.
This is Kamran, and today we're going to talk about big O notation. We'll talk about what the algorithmic complexity is.
Why is it translating to Hindi? Okay, I guess we'll have to do with that. Okay, let me just open this up again. Subtitles. Huh. I guess we'll just play the video as it is then.
Talk about big O notation. We'll talk about what the algorithmic complexity is and how we can measure the algorithmic complexity of an algorithm. Before we talk about the complexities, let's make sure that we know what an algorithm is. An algorithm is just a set of instructions to perform some operation. It could be a simple function, it could be a program that takes in some input, does some processing, and gives us the output. There are mainly two features of an algorithm that we are mostly interested in: the time it takes to run the algorithm and the space it takes in the memory. Algorithmic complexity is the measure of how much time it takes to run the algorithm, called time complexity, and how much space it takes in the memory, called space complexity. There are three different notations used to represent the algorithmic complexity: big O, big omega, and big theta. Big O refers to the behavior of the algorithm in the worst case. Big omega refers to the best case, and big theta refers to the average case and lies between the worst and the best cases. We are mostly interested in identifying the worst case behavior, because if we know how the algorithm behaves in the worst case, we know the quality of the algorithm. Alright, enough with the theory. Let's see how we can calculate the algorithmic complexity. To calculate the complexity of an algorithm, we just count the number of statements our program has to execute. Let's take an example of a function called askInfo, which is just printing a couple of strings to the console. If we count the number of statements in this function, it is 1, 2, 3, and 4. So we can say that the complexity of this algorithm is 4. This complexity is also called constant complexity because it doesn't depend on the number of inputs that the user gives. It is
What's that?
say that the complexity of this algorithm is 4. This complexity is also called constant complexity
Oh, all right. Constant complexity. Okay.
because it doesn't depend on the number of inputs that the user gives. It is always going to be 4 statements that it has to run. Such complexity is
Constant
called
type.
constant complexity, and we use 1 to represent this. So no matter how many inputs are given to this function, it is always going to be considered as 1. Let's take a different example where the complexity depends on the input given to the program. Let's say that we have a function called printItems that takes in the items, it goes through the items and prints them one by one to the console. And now if we count the number of statements that our program has to run, so we have the declaration, so statement count would be 1, and then for each iteration we perform the check to see if we have reached the upper limit of the items, so 1, then we get the item from the array, 2, then we print the item to the console, 3, and then we have the increment for I, so 4. So the statement count would be 1 plus 4n. So the complexity of this algorithm
1 second. Let me just do one thing here. Let me just ensure that the stream, yeah, is going to YouTube. It is. So yeah, let's continue. Oops, 1 second here. Sorry, guys. Okay, good. Let's go back. Let's listen to this again.
count the number of statements that our program has to run. So we have the declaration, so statement count would be 1, and then for each iteration we perform the check to see if we have reached the upper limit of the items, so 1, then we get the item from the array, 2, then we print the item to the console, 3, and then we have the increment for I, so 4. So the statement count would be 1 plus 4n. So the complexity of this algorithm is going to be O of 1 plus O of 4n. In the cases like this, when we have multiple complexities for the algorithm, we only take the complexity that has the highest significance in the complexity. So in this case, if we look at the complexity, 4n has the highest significance. So we can drop O of 1 and take 4n. Now in the 4n also, n has the highest significance because it depends on the number of inputs or number of items given to the function. So we can drop 4 as well and take n only. So the
And this, I believe, becomes linear time.
complexity for this function would be O of n. Here is the list of common complexity.
Linear, quadratic, constant, exponential, logarithmic.
That you might come across. We will now look at the examples of each to understand how to identify one and also see how an algorithm with the given complexity might grow. Alright, so first of all we have the linear complexity O of n. If you plot the graph for this where we have the inputs
It would
on
be
the
a straight line
x-axis and we have the time or space on the y-axis, the growth of a linear algorithm looks like this, which means that with the increase in the number of inputs, the time taken or space taken is going to grow linearly. So O of 1, for one input it's going to be 1, for 2 it's going to be 2, 3 is going to be 3, and so on. So O of n is equal to n. Here is the example of an algorithm with the linear complexity, where n is the number of items. So if we keep increasing the number of items, we're going to have one more item to iterate on. So there is a linear growth. Next we have quadratic complexity. In quadratic complexity, the time or space taken scales with each increase in the number of inputs.
Yeah, basically, in a way, if you have two for loops, right? Because for each nth iteration, you have to do another n number of iterations. So
What do we mean by that? If we draw the graph for quadratic complexity, the growth looks like this. So if we have one input, so O of 1 is going to be 1. But if we put 2, now we have 4. If we
for
put 3, we
iterations.
have 9.
Yeah, basically, I like to think of these as in a way number of iterations, right? Or effective iterations. So
4 is 16 and n is n square. So you can see that with the increase in the number of inputs, the time or space taken grows rapidly. The algorithmic example for this would be loop within a loop. So if we have n as the number of items, here we have the outer loop which goes from 0 to n, and then for each iteration we have an inner loop that goes through all the items again. Alright, so next we have constant complexity. In the constant complexity, no matter what the input size is, the time or
I guess that same concept can be used to plot out like quadratic. I'm not sure if you have a cubic complexity, but you could have n cube, n raised to 4, n raised to 5, and yeah.
or space taken remains always the same. So if we have one input, O of 1 is 1. If we have two inputs, it is still 1. If we have n inputs, it is still going to be 1. The algorithmic example for this would be a simple access of
Print
item
statement.
from an array. So no matter what is the size of the names array, the array access is going to be always taking the same time. Alright, so next we have the exponential complexity. So O of 2 raised to the power n. If we plot the graph for this, it is going to look like this. So with the increase in the number of inputs, there is exponential growth in the time.
Yeah, this is one of those worst case scenarios out there, right? Like it goes 2, 4, 8, 16, 32, 64, 128, and there is a problem given out to people. Like if you start from a penny and you could double it for 30 days and you could get, I believe it was a $1 million outright or something, what would you take? Yeah, I believe that was the question. Yeah, that was the either way, what I'm trying to say is this is a worst case scenario. So
Time or space. So for one input it is going to be 1, for 2 it is going to be 4, for 3 it is going to be 8, and n is going to,
for example, like if what is, just imagine you have 20 outputs, right? And that becomes, oh, alright, that's a huge number, and you just increase this by what, 10 more, and yeah, it gets out of control really fast.
to be 2 raised to the power n. The algorithmic example for this would be, for example, if you're iterating through all the possible combinations of items in an array. Another example would be Fibonacci series. So with the increase in n, it is going to grow exponentially. It would be if you're 2 raised to the power be 4, for 3 it is going to be 8, and n is going to be 2 raised to the power n. The algorithmic example for this would be, for example, if you're iterating through all the possible combinations of items in an array.
All the possible combinations. Oh, all right. I think he means something like, well, I don't want to create a file right now. Oh, you know what? Let's just create one. We're not gonna commit it. Just create a py file. We'll delete it afterwards. So let's just zoom in. Why am I using such? I haven't realized this, by the way. I don't know if my text for the other streams is very tiny. I'll have to look into that. But I guess what he's trying to say is if you have an array like this, right, all the possible combinations would look like what? This would be a possible combination. This can be a possible combination. Then this could be a possible combination. This and so on. And yeah, actually, how many combinations would there be? There would be what? 6 into 5 into 4 into 3 into 2 into 6 factorial, right? Or yeah, I have to see. But I think I understand what he means, and he's giving another example.
Another example would be Fibonacci series. So with
Fibonacci series without memorization, right?
the increase in n, it is going to grow exponentially. Next, we have the logarithmic complexity. In the logarithmic complexity, you can increase the number of inputs exponentially, but the time or space taken is going to grow linearly. So this is the next preferred complexity after the constant complexity that we saw. The number of inputs exponentially, but the time or space taken is going to grow linearly. So this is next
What?
we have the logarithmic complexity. In the logarithmic complexity, you can increase the number of inputs exponentially, but the time or space taken is going to grow linearly. So this is the next preferred complexity after the constant complexity that we saw before. So if we have 10 inputs, O of 10 is going to be 1. If we have 100 inputs, it's going to be 2. For 1000, it is going to be 3. 10,000 is going to be 4. And n is going to be log n. Here is an example of an algorithm with logarithmic complexity. So as you're going to be log n. Here is an example of an algorithm with logarithmic complexity. So as you can see here, with each next iteration, we increment I in such a way that we only have to look at half of the items in the array. Another famous example for this would
For I equals 1, I less than or equal to n, I equals I, you multiplied by 2.
city. So as you can see here, with each next iteration, we increment I in such a way that we only have to look at half of the items in the array.
Well, not even half, right? Not even half, like it reduces significantly.
Another famous example for
Maybe
this
I'm
would be
wrong.
the binary search. So we have a sorted array and we have to look for some, let's say, number in this array. So we start with the item in the middle and we check
We split
if the
it
item that we're looking
left,
for
right.
is smaller than this item, then we take the left half. If it is greater than the number, then we take the right half. So let's say that we have the item that we're looking for, it is smaller than this number. So we will drop the right half and only take the left half. And we will keep repeating till we find the item that we're looking for. Alright, so now
Yeah, in a way, we are getting rid of half of the items for each subarray, so it effectively becomes
to
this.
summarize, here
Sort
is
of
the
makes
list of
sense, yeah.
complexities that we have just seen. If we plot them all in one graph, the complexity of O of n is going to look linear like this. N squared is going to
Let me
look
see if
like
I
this.
can
The constant complexity
make
O
it
of
out.
1 is going
Straight
to look
line.
like this. Exponential complexity is going to look like this.
And even
here is how the logarithmic complexity
not,
is going to
I don't know
look
if
like.
that should stay steeper or, yeah, I have to get that term right, but I understand.
If we compare all these graphs and see with the increase in the number of inputs how the time and space usage grows, here's how we can sort all the complexities from the best to the worst. So constant complexity is the best. The next one you should
Oh, I think I mentioned that this comes after this, but yeah, this comes before I.
aim for is the logarithmic complexity. After that we have the linear complexity and so on. And that is all for this one. Comment below if you want me to make more.
Alright, thank you for this. That was a really good summary. Now let's go into, oh, there's also a video for this by CS Dojo. But let's do the free code cam one. Although I'm 100% sure this is gonna be a really good one. So maybe we'll do this. We'll see, but let's do this one now.
O notation is used to classify algorithms based on how fast they grow or decline. It is very important to understand for many types of programming. Giorgio Tunson does a great job of breaking down Big O notation in this course.
Hey, what's up everybody, and welcome to my mini-series on Big O notation. In this mini-series, you'll learn everything that you need to know about Big O notation and how you can use it to improve your ability to create efficient algorithms. I'll use whiteboard illustrations to help you visualize and understand concepts of efficient algorithms.
Look at that graphic. I believe this graph is taken from the wiki page. Well, let's just do a wiki search for this. Big O notation. So, let's see. Let me just. Okay. Never mind. I was wondering whether to plug in my lab, but maybe I'll do it after a while. Um, so, mm-hmm. Oh, O means what? Oh, Ordnung? How do you pronounce it?
Ordnung.
Ordnung. Ordnung.
Ordnung.
Ordnung.
Ordnung.
Ordnung.
Ordnung. Well, now I can say what the O in, or at least where the O in big O came from. Right? When the big O notation is often used to. Alright. Yeah, big O is basically an estimate, right? A way to represent an estimate. Then there's omega, theta notations. Let's see if we can find in computer science, it is useful in the analysis of algorithms. Let's just open that up. Yeah, I'm familiar with what an asymptote is. It's like when, yeah, I don't know exactly how to or put it in mathematical terms, but it's like the graph of one of the. I'm just graph of tan in some value, right? Like it goes beyond, like it goes into infinity, and you sort of draw a line. So because infinitesimal is the opposite, like it approaches what approaches a number or something. Okay. So let's see. This is more of the well, okay, we got a constant time. Okay, this is used also logarithmic time, finding an item in a sort either with a binary search or a balanced search tree, as well as all operations in a binomial heap. Then you have what? You have log n raised to something. It has a name, polyalgorithmic matrix chain ordering. Can be solved in polylogarithmic time on a parallel random access machine. VRAM. Okay, alright. Then of course you have you have fractional power searching in a KD tree. Okay, anyway, let's go to the main ones, which is linear finding a yeah. You have n log n. That apparently comes in this. Or what is that? Seidels algorithm. You have n square. Multiplying two n-digit number by school book multiplication. It's the algorithm that you're taught when you're in elementary school, right? Yes, it is. It is? Yeah. Maybe that's what it means. Symbol sorting algorithms, bubble sort, selection sort, insertion sort. Okay, then of course anything greater is polynomial time. Determinant with LU decomposition. I've heard that somewhere. Then factorial time. Solve the traveling salesman problem via brute force approach. Okay, this is a famous problem, isn't it? And I'm pretty sure this will come up, and yeah, we'll study it. Exponential, which is 3 raised to n, or it can be 2 raised to n, 3 raised to n, whatever. Where c is a constant, basically, right? Then there's something else, little annotation. Alright, let's just go ahead and search for. Oh, this leads to the same page. Okay, let's just go back and yeah, let's assume that was that was something. Alright.
I'll use whiteboard illustrations to help you visualize and understand concepts, followed by coding tutorials that you can follow along with to further solidify your grasp of the concepts. We'll answer the question, what is Big O notation and why is it useful? So what is Big O notation? Big O notation is used to analyze the efficiency of an algorithm as its input approaches infinity, which means that as the size of the input to the algorithm grows, how drastically do the space or time requirements grow with it? For example, let's say that we have a dentist, and she takes 30 minutes to treat one patient. As her line of patients increases, the time that it takes for her to treat all of the patients will scale linearly with the number of patients waiting in line. This is because it always takes her a constant amount of time to treat each individual patient, which is 30 minutes. This gives us a general understanding of how long our dentist would take to treat 10 patients, 20 patients, or even 100,000 patients. This is because since we know that the dentist takes a constant amount of time, which is 30 minutes, to treat each patient, we can always calculate the time it would take for her to treat any number of patients by multiplying the number of patients times 30 minutes. With this in mind, we can categorize her efficiency as being linear, or as we would say in Big O terms, Big O of n, where n is equal to the number of patients. The time that it takes for her to finish her work scales linearly or proportionally with the number of patients. We use this same technique to determine the efficiency of algorithms. We can get a general idea of how a function's time efficiency scales by categorizing a given function's efficiency the same way that we categorize the dentist's efficiency. Let's create an easily comprehensible function that scales similarly to the dentist's. So this function is in the same linear category as our dentist. Let's step through it and find out why. To start, the input to our function is an array with 7 items inside of it. For each of those items, we will log this expression which multiplies 1000 times 100,000. Now don't let these large numbers fool you. It will always take the same amount of time to multiply 1000 times 100,000. Therefore, this line of code takes constant time. Which brings me to a very important point. When considering the efficiency of a function, these lines that take constant time do not matter. Well, at least for our purposes they don't. This is because if our array were some crazy length like 200 million, changing this expression to something simpler like 1 plus 1 would have a negligible effect on the efficiency of the function as a whole. We'd still need to iterate through 200 million items in an array. In fact, even if the function looked like this, we would still ignore all of these constants and say that this function scales linearly or is big O of n. Similarly, if we think back to our dentist example, we see that she took 30 minutes per patient. But even if she took 3 hours per patient, the amount of time it takes her to see all of her patients will still scale linearly. This can be difficult to grasp at first, but it starts to make sense over time. So in the last slide, there was a lot of talk about ignoring the constants, but what exactly is a constant? A constant is any step that doesn't scale with the input to the function. For example, the time to evaluate this expression does not change with the input because both
Yeah, array can be whatever, like length, but it doesn't matter.
100 and 1000 are constants. That is, these values are always the same. This expression always results in the same value, and it always takes the same amount of time, or constant time, to return the same result. Just like we use big O of n to describe linear functions, we also have a big O name for constant algorithms, which is big O of 1. A good way to think about it is, every line of code is actually a function in and of itself, which is actually true. For example, let's reintroduce this function. So this line of code is the reason why the entire linear function is O of n, because as you can see, as the size of n increases, the number of iterations that the for loop must traverse increases as well. But let's take this second line into consideration. Let's for 1 second pretend that we have a function that contains only this line. Now as you can see, with this function, we pass in an array, but the function does nothing with the array. The only operation...
That's a new way to think about this. Treat every line as a function and then evaluate it. Yeah, that's a new perspective.
Within the function is constant because it doesn't scale with any input.
So regardless of how large of an array is passed to this function, this line always produces the same result, and this is the only line in the function, so therefore this entire function is O of 1. But wait, in this function we have multiple lines that are O of 1, yet we still prioritize the line that is O of n and ignore the O of 1 operations. Why is this? Well, this brings us to our last important.
Oh, we have a chat here. Hey there, I hope to be one day. I remember you were there in the Codewars stream, right? Also, I did get your, you posted a problem, lead code problem, but I wasn't in the second monitor of mine. I've, if you check my GitHub, I've actually put that link in there. I'll try to solve it one day. Thank you. If you don't mind me asking, are you a developer or a student or?
Note, in Big O we have a growth hierarchy which looks something like this. Now don't panic, you don't need to understand all of these just yet. So let's only pay attention to the ones relevant to this video.
Alright, that's amazing. What do you do? I guess what I'm trying to ask is, are you a web developer or game developer or what do you do?
O of n and O of 1. We'll learn about the other.
Or maybe a jack of all trades developer. Yeah, that role, really exists. A backend developer. Okay, cool. I'm assuming through Node. Oh, well, I work as a developer too, obviously. I started freelancing and right now I act as a web crawling engineer. Although I also do API development, so somewhere in between. It's great to have you here, Anyhow, my main aim is to, get into ML. I know I've been saying it out quite a lot. I hope to do, reach that stage one day. I'm also interested in web development and everything too. Oh, thank you. This is actually my, it was my balcony and I transformed it into this sort of like my personal space. I guess you can call it an office, but
in following videos for this series. This chart shows the efficiency categories in order from good to bad. That is to say that this first case, O of 1, is the best case, and this last one is the worst case. In Big O notation, when determining the efficiency of an algorithm, we only care about the worst case. So that means that the worst case, or the highest order.
yeah. And what was the so in Big O we trade with the bad, like we only care about the worst case scenario. What was the one which looks at the best case scenario? I believe it was is it theta or omega? Maybe theta is the average, I guess, and I guess it's omega, right? Yeah, omega is the big omega, big omega notation. All right.
Order operation trumps the operations that have better performance. So if we add the performance of all of these lines up like so, all of the lines of code that are O of 1 get cancelled out because O of n is the worst performing or highest order part of the function. And this, ladies and gentlemen, is why we ignore constants. Because we're actually just eliminating the non-dominant items, because as a function's input moves towards infinity, constants become less and less significant. So to recap, when evaluating an algorithm's efficiency, we must take into consideration the efficiency of each step within the algorithm. We then find the highest order step, or the step that has the worst performance, and prioritize it over all of the better performing steps. Steps that are constant or that are O of 1 are as good as it gets in terms of efficiency. So we always ignore them, unless the entirety of the function is constant or O of 1. And in that case, we would categorize the entire function as constant or O of 1. And that, ladies and gentlemen, is your answer to what is Big O notation.
Oh wait, what? I thought this was another ad when immediately switch from this to that Blackboard segment.
Ladies and gentlemen, is your answer to what is big O notation? Okay, so to understand O of n squared, we're going to need to take a function into...
Oh, let's just look at the chapter names real quick. So we have what's this called? Quadratic complexity, then cubic. We have logarithmic. What was this called though? It was covered in that Wikipedia page, right? Guess we'll come to it. Then we have exponential, we have factorial, and okay. Yeah, common mistake segment to end it.
consideration. And the function will look something like this. So what this function is doing is it's going to take in a number n, and it's going to iterate through this for loop, starting with the number 0 all the way up until the number n. And for every iteration of this top for loop, we're also going to loop through this nested for loop. And this nested for loop is doing the exact same thing that this for loop is doing. It's iterating through every number, starting with 0 up until the number...
Should I write this? Let me just, I know that this doesn't, yeah, it has a coding segment, coding binary search. And most of it is covered in Node itself. I mean, not most of it, all of it is covered in Node.js. I guess this repo is gonna consist both of Node, Python, and maybe, if possible, maybe some other language that I may pick up. So I guess we'll just write it as an example, right? I mean, we're learning. So first and foremost, let's delete this file over here. And how do I structure this? I guess I can create a folder and then put everything related to Big O in that folder. So I guess we can, rather than calling it Big O, we can just do that. Makes that makes sense. So so what's actually being covered right now? It's exponential, right? But let's also write down constant time and linear time there. Show. This is show. I meant so. Constant complexity. Well, let's not do. Let's just do constant.js. You know what? Let's just be explicit. I don't think many people would catch this. So, how do I rename this? Huh? Can't I rename this? There we go. Big O. Let's have constant. Yeah, we'll do some restructuring later, but let's end it with complexity. So this is gonna be let's create a function. Let x equals I guess we can call constant complexity, and that should do it. I guess we can just cd into this and then run node. I guess I have to save this, right? Okay, there we go. Now let's have linear complexity. Just copy this function and then edit it. And I guess we can also be more explicit with this. This would be off 1. This would be off what? Off n. Well, it's not off n right now, but we'll make it linear time. So to make it linear time, let's yeah, let's have an array defined because I feel we're gonna need it for at least the next few cases. So let array equal, we'll have 1 through 10. And we'll call linear complexity, and then obviously we have to pass in the array now that it's actually I guess not doesn't care if it assumes it's default, I mean undefined by default, doesn't it? Anyway, let's go back and let's have a for loop. Then we can have I less than array dot length I plus plus console dot log I, and we'll also access array I. And let's run this. And let's also ensure that the previous one, constant complexity, is, yep, it's running. Now let's have well, what should we have? What's next? I believe it's constant linear. It should be, well, it should actually go like constant logarithmic linear, but let's see what's next.
Number in
It's
and
quadratic.
within this nested for loop where console
Yeah. Let's create one quadratic. How do you spell it? I guess this is the correct spelling, maybe. Well, actually, is it the correct spelling? I'm having second doubts here. Cool. Yeah, it is the correct spelling. I mean, who cares about spelling? But still, let's be right wherever we can be right. Yes, for this one, we'll just copy this loop again. We'll remove this. We'll have let's see. So we can have I, J, and array I. Well, I guess we need to have array J now. So this should be n square. And let's run this. I have a feeling I ran into an infinite loop. Why? What could have happened here? Oh, this needs to. Yeah, I'm not incrementing J, am I? All right. Now that's quadratic. The other one was infinite complexity. I'm gonna make up my own now.
So logging
Yeah,
the
let's go back.
coordinates for a cell within a matrix. But to make things clear, instead of illustrating a console log of the index I and j, I'm just going to draw a square where these coordinates should be for every iteration of this nested for loop. So if it sounds confusing, just try to bear with me. I promise it'll become clear. Okay, so let's say, for example, that we call the square function with the number 4. So that means that we're going to iterate through this top for loop starting from 0, and then we're going to iterate all the way up until I is no longer less than 4. Once I becomes equal to 4, then we will stop the iteration. And then that's only for the stop for loop. For each iteration of this actual for loop, then we're going to loop through the entirety of this nested for loop and do this console log.
I think for the first part, we'll just put it into X.
Coordinates, like I said, we'll draw a square where the coordinates would be, so you guys can visualize this better. So let's go ahead and get started. So for the first iteration, I is going to equal 0, and then we move on into this nested for loop, and then we're going to iterate through the entirety of this nested for loop. So right now, I and j are 0. So I and j are both 0. So we're currently at the first iteration of this for loop and the first iteration of
Alright, I'm gonna take a break here real quick. I'll be right back. Never mind. That was a spam call. I had a call that went, and although it's we have 40 seconds left till our break, so you know what? Might as well take it. So see you in 5 minutes. Alrighty, I'm back. Let's continue.
This for loop, and we'll draw a square. And then we move up one iteration of this for loop. So j becomes 1, and we'll draw another square. And then j becomes 2, and we'll draw another square. And then j becomes 3, and we'll draw another square. And now j is 4. And since j is 4, that means that j is no longer less than n, because n is 4. And j is 4, and n is 4, so j and n are now equal. So we'll no longer iterate through this for loop. So now we go back up to this for loop. And now I is equal to 1. So I is equal to 1, and j is equal to 0. So we'll
Yeah, I implemented the same thing too, except n is sort of like the array road length, which is also a constant. So
draw a square. And then I is equal to 1 and j is equal to 1, so we'll draw a square. And then I is equal to 1 and j is equal to 2, so we'll draw a square. And I is equal to 1 and j is equal to 3, and we'll draw a square. And now back to this top for loop again, because j and n are now equal. We're back up to this top for loop again.
oh, that's also another perspective, I guess, because at the end of this, it will form a square, right?
I is equal to 2. So I is equal to 2, and j is, which is equal to 3, j, and our n is
A
actually
square
equal.
of
We only
side
iterate this
n.
top for loop as long as our I is less than n, but our I is now equal to our n. So now we stop iterating through this top for loop. And what we're left with is this matrix here. And the reason why I said that these are coordinates for cells within a matrix is because this here is a matrix. And these are rows, and these are columns. So we can look at I as being our column.
I can't
And we
spell
look at J
too,
as being our
so
row. So for each iteration 0, 1, 2, 3 of our column, we also have an iteration for our row 0, 1, 2, 3. So coordinates being 0 and 0 were the coordinates for this square, and then 0 and 1 were the coordinates for this square, and 0 and 2 were the coordinates for this square, and so on and so forth. So what does all this have to do with O of n squared? Well, hey, just one quick interruption. If you are finding this video helpful or it's bringing you to some type of understanding, please take the time to like and subscribe. If we think about it, this is a square matrix. That is, each side will be of the same length. And by length, I mean 1, 2, 3, 4. This is of length 4, and 1, 2, 3, 4. And this is of length 4. And to find the area of a square, we just need to multiply the length of one side by itself, because every side of a square is of the same length. So if this were a rectangle, we would multiply the width times the height. But for a square, we can just multiply by itself, because the width and the height will be the same length. So to get the area of this square, we're just going to multiply 4
16.
times 4. 4 times 4. And that's going to equal the number of cells within this matrix, which also happens to be the number of times that we have to perform this code, which is 4 times 4 is 16. And 4 times 4 is the same thing as 4 square. So O of n square, our n is actually 4. And that is why typically functions with nested for loops, like a for loop and a for loop nested within it, like this function, is considered O of n square. I hope that makes sense. Okay, so to
Yeah, that same logic is gonna be applied to a cube, right? Except you also build upwards now. So let's see, let's create our own first, so we can do cubic complexity, I guess that's what it will be called, if I could spell right, that is complexity.js. Copy this, and then ig, let's have k next. And cube, and let me change the function name real quick. I feel that let me minimize the panel towards the left, the explorer, and the terminal too, at least a bit. Let's save this, and oops, yeah, let's save and then run this, and okay, that ran in cubic time. I know that didn't feel much like cubic time, but as this array is say to a million elements or something, it will be like it will take a very long time. So
understand O of n cube, let's take a function into consideration. This cube function takes in an argument in, which is a number, and it's going to iterate through this for loop. And for every iteration of this for loop, it's going to iterate through the entirety of this for loop. And for every iteration of this for loop, we will need to iterate through the entirety of this for loop. And I'm going to have to apologize ahead of time for my disappointing drawing skills. But to illustrate this, I'm actually going to have to draw three-dimensional shapes, which is not something that I'm entirely good at. But anyways, for now, the number in cube.
I think I get it with.
Because here, so
We'll just fill it up with squares.
and so but
I mean, not squares, cubes.
Point, increment 1, and j will then be equal. It's getting hard to see the cubes that I'm drawing here, and that's the volume. So O of n cubed, our n is 4, so O of 4 cubed, which equals
64,
which is the volume of this cube, which also happens to be the number of times we would perform this function, console log the coordinates, but in our case we just drew the squares. And that is why this function is O of n cubed.
Now we get to logarithmic.
We must first understand what a logarithm is. Simply put, a logarithm is the power that a number needs to be raised to get some other number.
Yeah.
I know, that doesn't make much sense out of context, but don't worry, I've got you covered. Let's take the number 8 into consideration. So we want to raise some number to some power to get 8. In computer science, unless specified otherwise, we can always assume that the number that we want to raise to some power is 2. So let's rewrite this. So we want to raise 2 to some power to get 8. So this same equation
That would be
like
3.
this, where this 2 here is called the base. And let's not forget that in computer science, the base is always 2. So to find the answer to this, we just need to find the answer to this. With that in mind, we can see that if we raise 2 to the power of 3, we get the number that we are looking for, 8. So log base 2 of 8 is 3. So with all of that in mind, let's move on to the meaning of O log n. For this portion, we will be using a very bare-bones recursive function to visualize O log n, but don't worry, I will walk you through every step. Just stay with me. So we will start with the number n. We will use 8 so that you can easily see how this relates to our explanation of logarithms in the previous slide. So this variable n, we will be passing to our recursive function that looks like this. So this function's time complexity is O log n. Let's dig deeper to find out why.
If n equals 0, return done. Else we half the value of n each time. And when we return log function again, until n becomes 0. It becomes 0 point. It becomes a decimal point, and then floor will just convert it into a 0.
For now, let's just ignore this first line and focus on what the function is actually doing. So when we pass a number n to this function, it divides n by 2 or splits it in half and then calls itself with the new halved or divided number. Let's visualize this using a graph. So we first call the function with the value 8. This 8 is then divided by 2. The function then takes the result of the division and passes it recursively to itself as the new value for n, which in turn results in us going one level deeper. We then do the same thing with our new value for n, which is 4. That 4 is divided by 2, resulting in a new n, and the function then passes our new value for n to a recursive call to itself again, resulting in us going one more level deeper. We then do the same thing with our most recent value for n, which is 2. We divide it by 2, and the function once again recursively calls itself. At this level, we will stop as we can no longer divide n without getting fractions as the result. Now we have arrived at the beginning of the secret to understanding O log n, so watch closely. If you look at our graph, you'll see that we've gone 1, 2, 3 levels deep. If you recall from our previous slide, the log base 2 of 8 is 3. Our input n is 8, and we've gone 3 levels deep. You will also notice that we have to raise 2 to the power of 3, or multiply 2 times 2 times 2 to get 8. And since division is just the inverse of multiplication, we can see that when we do something like this. So that means that this function has a time complexity of O log n. Why? Because our n is 8, and in computer science, our base is always 2. And we must have our n 3 times, or go 3 levels deep in our recursive function to get to a point where we can no longer reasonably have our input n, which is another way of saying that log base 2 of 8 equals 3. And that, ladies and gentlemen, is the secret to understanding O log n time complexity. And as a quick note, this is not only applicable to recursive functions. And if you're curious about that line of code that we covered up earlier, all it does is make sure we stop dividing n when n becomes 1, or otherwise the function would keep dividing fraction after fraction until we eventually exceed the maximum call stack. So we'll start with a very simple function, which contains only a while loop that assigns a new value to the variable n for each iteration. And for this example, let's imagine that we're passing the value 8 to our n for this function. So that means we'll iterate through this while loop as long as 8 is greater than 1. And for each iteration of this while loop, we're going to divide our n by 2 and reassign it to n. So our n is going to be halved for each iteration. So currently our n is equal to 8 because we passed in 8 as n. And while n is greater than 1, we're going to iterate. So right now n is 8, which is greater than 1. So we'll do this math.floor n divided by 2 for our first iteration, which would set our n equal to 8 divided by 2, which is 4. And this math.floor, all it does is it floors the result of our division. So for example, if we have math.floor 5 divided by 2, we would get 2 here instead of 2.5. So after this first iteration, our n is now equal to 4. So while n is greater than 1, we're going to do another iteration. So 4 is greater than 1. So we're going to do this again. And n is going to equal 4 divided by 2, which is going to equal 2. So now our n is equal to 2. And while n is greater than 1, we're going to do this again. So n is currently greater than 1, 2 is greater than 1. So we're going to do it again for a third iteration. So n is going to equal 2 divided by 2, which is going to equal 1. So at this point,
our n is equal to 1, and we're going to go to this condition here again. So while n is greater than 1, we're going to do this, but right now n is equal to 1. It's no longer greater than 1, so we're not going to continue with this while loop. So why is this function o of log n? So our n is 8, so that means that this function should be o of log 8. And if you remember from the previous video on O of log n complexity, this is just the same thing as
iterations,
O
right?
of log base 2, 8, which just means what power do we need to raise 2 by to get 8? And if we write this out, what power do we need to raise 2 by to get 8? We see that we need to raise 2 to the third power to get 8, because 2 times 2 times 2 equals 8. So this 3 is what's important, because division is just the inverse of multiplication. So if we need to multiply 2 times 2 times 2 to get 8, then we should also be able to divide 8 by 2 3 times to get 1. So there's 1, 2, 3. So that means that for this function, when we pass in a value for n, we're always going to need to divide this value n by 2 log n times before we can get 1, which is just another way of saying that when we pass into this function, we're going to iterate through this while loop log n iterations before we get to the value 1. So if you see here, we have 1 iteration, 2 iterations, 3 iterations. So there's 3 iterations here. So this 3 is log n iterations, because again, O log n just means O log base 2 of 8, because our n is 8. And log base 2 of 8 is 3, because 2 to the power of 3 equals 8, which is our n. And that is why this non-recursive function is O log n, because there will be log n iterations, 1, 2, 3, before this while loop ends. I hope that makes sense.
So that makes sense. Let's just quickly go ahead and write this down. It doesn't make sense for this to have an array here, right? So let's just put n here. We're gonna assign n to math.flow and let's just console.log. Let's actually do a do while loop, right? Because we want the do console.log and while n is greater than 1, and then assign n equal to math.flow. Runs in logarithmic time of log n. Let's have let n equals, let's just do 64, and let's pass in n here. Obviously change this from quadratic to logarithmic. Let's check. So let's run node logarithmic complexity, and what happened? While n is greater than 1 or less than 1. Oops, it's running in a infinite loop over there. Oh, I am not dividing this by 2. Okay, that should work now. Great, and that's right, because 64 is what, 2 raised to 1, 2, 3, 4, 5, 6. The 2 raised to 4 is 16, 5, 32, and 6, 64.
To start, we should understand that in order for binary search to work, the array that you are searching must be an ordered array. Both ascending and descending ordered arrays will work. Let's start by visualizing our array. In practice, this is much more useful as the size of an array becomes much larger, but we will stick with an array containing 9 elements to help us understand the concept more clearly. So let's assume that we want to check our array to see if the value 100 exists inside of the array.
We'll start at the midpoint. We'll check this. If this value is less than the value that we want to search, we check only the right side of the array. We again take the midpoint, check the right side. And if it's equal to or less than, then we check the left side. And if it is equal to, then we just return it. I mean, we return true, I guess. Or we return the value.
Iterate through each element of the array, checking to see if the value is equal to 100, like so. But for this method, we have to iterate through every element in the array up until the value that we're looking for. What if we have to do this for an array containing 1,000 or 100,000 or even 1,000,000 elements?
And what if it's a sorted array, right? If we already know that the array is sorted, then use binary search.
This is where something like binary search can be useful, so let's try this again. So here, we're still wanting to check to see if the value 100 is in our array, but this time we'll use binary search to figure this out. To start, we need to find the midpoint of our array, which is just the element in the middle of our array. Our midpoint is here. Now, since our array is in ascending order, we know that anything to the right of our midpoint will be a value that is larger than our midpoint. And everything to the left of our midpoint will be a value that is less than our midpoint. So we need to figure out if this number, 100, which we are searching for, is greater than or less than our midpoint. This will tell us which side of our array our number is on. So if we simply write out 43 is less than 100, we can actually see that the side of the array that our number is on is this side. To paint a full picture, let's for 1 second pretend that the number we are searching for is 2 and not 100. In this case, 2 would be less than our midpoint, 43. Therefore, it will be on the left side. And this, ladies and gentlemen, is why binary search will only work on ordered arrays. Because without the order, there would be no way to tell which side the number we are searching for is on by comparing it to the midpoint. Now let's get back to the original number that we were using for our example. So now that we know that 100 will be on the right side of our midpoint, we can completely do away with anything to the left of the midpoint, including the midpoint. So what we are left with is this. What we've done is we've essentially cut the array in half. To put this in perspective, let's imagine that we have an array with 1 million elements and we divide it by 2. In just one step, we will have cut down the number of elements that we would need to search by 500,000 elements as opposed to iterating through all 1 million elements and searching that way. And it doesn't stop here. We will now do the exact same thing with this half of the array. Let's remember that we're searching to see if the number 100 exists within our array. We will first need to find our midpoint. Now don't be confused by the even number of elements in this array. Although there won't be an even number of elements on each side of our midpoint, it does not actually matter because we actually just need to split the array approximately in half. For example, to find the mid in code, we would do something like divide the length of the array, which is 4, by 2. That resulting 2 we would use as the index of our mid. So let's write out the indexes of this array, remembering that arrays are 0-based, meaning that the starting index will be 0. And if we take this resulting 2 and see what value it points to, we see that our mid is 100, which is the number that we are searching for. So in that case, we would be done. We have found our number. But to prove that which one of these we choose to use doesn't actually matter, let's explore what would happen if the mid 54 were used. Is the number that we're looking for greater than or less than our mid 54? Our number is greater than 54, so that means that we can get rid of the left side. And what we're left with is an array containing only 2 elements, which again is an even array, so we have no way of determining which one we should choose as our mid. Let's see what would happen if we use 124 as our mid. Is 124 greater than or less than 100? It is greater than, so we can ignore the right half of this array. Now we're left with an array containing only 1 element, so our so-called midpoint can only be this element. And this element is the number we're searching for, so we're done here. So as you can see, regardless of if you have an odd array or an even array, as long as it is ordered, the searched for element will be found if it exists in the array. And that, ladies and gentlemen, is how binary search actually works and why it is useful. So let's just start by creating a file, and we can call it login.js. For binary search to work, the array that we're searching must be in either ascending or descending order. So you can't just have a randomly ordered array and use binary search on it. So that's just something to keep in mind throughout the rest of this tutorial. Our binary search function is going to take in...
Let's actually create a algorithms folder here. Because looking at the chapter names, merge sort is also coming up. And maybe there might be something else we can put in there too. Oh, in that case, I guess we could create a folder specifically for all the complexities. And then we can also create algorithms. Let's create binary search.js.
4 arguments. It's going to take in an array, and the array is just going to contain integer values, which will need to be ordered. So we will just do 1 through 8.
Right.
We'll also need to pass in the first index of our array to the function. We'll just call it start. And that's just going to be 0. And we'll need to take in the last index of our array, which we'll just call end. And we can get that by getting the length of the array and subtracting 1 from it. The reason we need to subtract 1 from the length of the array is because the indexes of the array are actually 0-based, but the array itself, the length, is actually not 0-based. It's just going to be the number of elements in the array. So the array length is going to be 8, but the last index of the array of length 8 will be 7. So that's why we subtract the 1. And then last but not least, we'll need to take in a target value, which is the value that we're searching for. And we're going to just search for 8. And then we can start building our function. And we'll just call it binary search. And it'll take in the array, the start, the end, and the target. And this function is actually going to be a recursive function. So to start this function off, we need to find the middle index of our array. So you'll notice that we're using a built-in function math.floor here. And the reason we're using this is because if we go to the definition, it says that it returns the greatest integer less than or equal to its numeric argument, which basically just means that if this division expression within our function parentheses returns something like 5.5, the value assigned to mid would only be 5, because we don't want to take into consideration anything after the decimal point, because we just want to find an index, which of course there wouldn't be an index 5.5, so therefore our mid would just be 5. And the next thing we would want to do is check to see if our midpoint is actually the number that we're searching for, which is our target. So this would basically return true if the mid value of our array is actually the target that we're looking for. So we're returning true because that means that the value that we're searching for exists within the array, and we would be done here. And actually, I just realized I might actually be confusing you guys by referring to our mid and our mid value interchangeably. So this mid here is actually the index of our mid, which is what we're trying to get. We're trying to get the index. So here we can just add index as well. So when I say our mid, I'm actually referring to...
How would this exactly... Oh, because, yeah, we are not updating the start and end, right? That makes sense. I mean, we are not updating it right now.
to the value. So we actually want to return true if the value...
Let's look at the video first, and at least a bit, and then we'll go...
We then want to go on to check to see if the value at our mid index is greater than or less than our actual target. So...
What is index mid? It should be mid index, right?
This should be mid index. Sorry about that. And actually, we have another error here. So till start, and then target should be here, and that should. Work. So yeah, let's take the time to understand what's happening in this line of code here. So if the value at mid is greater than our target, then that's going to mean that our target is actually in the left side of the array. Because if we look here and we take into consideration that 5 is going to be our mid in this situation, in the first execution of this function, 5 is going to be our mid. And if 5 is greater than the number that we're searching for, then that means the number that we're searching for is going to be in the left side. Because if the number that we're searching for were greater than 5, then it would be in the right side of the array, because our array is in ascending order. So this is to check to see if the item that we're searching for is in the left side of the array. And if it is, what we're going to do is we're going to pass in our start, which is going to remain the same. So we're going to keep the same start, which is going to...
Else we're gonna keep the same end, but the start is gonna be equal to mid plus 1. Yeah, that makes sense. How do I... Yeah. Alright, so if what did we call our array? Okay, array mid. Yeah, let's call it mid index itself. Equals our target. Then we return true. Else we're gonna check if let's not do one-liners for the time being. Let's make it more I guess interactive, not interactive, but yeah, more so that the output looks better, you know. So found target at mid index. Now else if the array the value is less than the target, less than what we want, we're gonna just cut everything off from the left side, right? So let's just return binary search, and we're gonna pass in the array again, but our if our array mid index is less than target, if it's less than our target, then the value is on the right side. So the start would be what? Yeah, it would be mid index. I want to do +1, but what if the value is all the way to the right? I guess it does make sense. Then the end would be what? The end would be still end. Then of course we pass in the same target. Else it's simple, we just, yeah, we return binary search again, but this time we keep the same start, but we subtract the end here. And let's run binary search on our array start and target, and let's cd into algorithms and not binary search found target 8 at 7 at index 7. Let's make that clear. At index 7. Great. And no, that works. Let's see what else would we have. But what if we want to return false? Like, what if the value is not there, right? We can return true here. Yes, we have a base condition which says okay, let's do this out by hand. So let's say we want to find the value 6. Let's just assume 6 isn't here. So we cancel this first, then we look at this. We come to the mid, which may be here. We cancel this. We come here. We come to the mid. We cancel. Oh, actually, if we come here, huh? I guess okay. We come here. We cancel this. We come here. We cancel this, and at the end, undefined. Then we return false. Let's wrap this in bracket. And let's try to find 6 here. Maximum call. Okay. Let's look at what
to be in
the
this case, it's going to
condition
be
is.
0. And then our end is going to be
Fine.
min -1.
As
1
per,
we need
yeah.
to assign only these would have a target on our going passing where because it's
Mm.
acting order. So it's going to be on this right side. And this value for only search of our mid, search is for slice. We're going to array. So we will try and run it by just using node login.js here. So it caused the entire function to fail. Forgot to add in the target here. So it called. Okay, and we get true this within the array. We're going to some call stack side. So pin does not exist. So let's try it again.
Does not exist. Okay.
And we get.
I mean, yeah, it doesn't
eight is
exist,
found
but
within the array. But what you'll see here is if we search for something that doesn't exist within the array, we're going to break it again. So 10 does
Yeah.
not exist. So let's try it again. And we got maximum call stack size exceeded because let me show you what it means. We're calling the function recursively calling itself again. It's going to be a point which is that will greater than. If the target's not in our array, it either means that the target is larger than the largest value in our array or it's smaller than.
oh yeah, we can. I see. So we can have this as the condition, right? Rather than having this, because yeah, we can have a start is greater than n, then it is not a valid array, meaning we've exhausted all options, and then we can return this. And we can also console.log target not in array. And let's return this back.
than the smallest value in our array. So that means our function will keep checking our array until eventually we get to either the largest item if the target is larger than the largest value in the array, or it gets to the smallest item if the target is smaller than the smallest item in the array. And at that point, the start and the end values will be equal. And at the point where both the start and the end values are equal, passing our start and our end to either this line or this line will in effect make the start greater than the end. And now we can run this again using this 10 that doesn't exist within our array. And as you can see, we get false. And if we even added negative here, oops, negative 10 doesn't exist, so we get false as well. And let's see. The feel for why this function is ologin, let's go ahead and create a longer array here. So currently it's I can just do less than or equal to, and let's see. Okay, so at this point we have a longer array, which will hopefully help for you guys to visualize how the input is scaling when I do some console log trickery here. From 1 to 1000 the array, so we'll just put like here, please still be 0 log. So we're gonna execute the function here, and then here is where we're going to try and make some magic happen. So I want to add slice to the end. It's not going to show the full array anymore again. Okay, and yeah, that worked. So maybe I can make this smaller so you can see. So when I make it smaller like this, it's kind of easy for you to see, like,
Yeah.
well, at this point the array is too long to show its entirety, but you can still see what's happening here. So like, since the value to get color, this function has a complexity. What's happening here, like you can see that the array is continuing to get smaller and smaller. To understand O of n log n, we will take this small function into consideration. This